Okay. So today what we are going to start with is non-parametric statistics. I keep on asking this question, right? What are the assumptions of t-test and all?
Assumption of alpha is that all the variances between the groups is same as the overall variance.
This is the hypothesis we are testing. What is the assumption?
Normal distribution.
Normal distribution. T-test also normal. No? Yes. And the type of variable?
Both continuous.
Continuous. But continuous are of different type, right? Which type is this? Which type we test? There is a nova and t-test.
The output is.
The output? The output is continuous? Okay, good enough. Do we test ordinal with t-test and nova? T-test, we can test ordinal? No. It's a ratio type. Okay, ratio or the interval. Okay. So these are the assumptions. But the main one is normal distribution, obviously. And then others are also important. We mentioned the hypothesis about the values. But what if I have data that does not follow these assumptions? Not normal distribution, or it's not continuous, or it's continuous but it's not ratio or interval. It is nominal or ordinal. And what should we do? So we need, yes. So we need different set of methods which can fit into this table. Now, you are taking the other course, AI, right? What's the name of the course? Yeah, right. Those techniques can indirectly give you the testing as well. Okay. Now up till now we have done tests and models. Okay. These two are what? T-test and ANOVA. Test or model? Test. And what are the models? Linear regression. Polynomial. What was the last one? For categorical data. Multiple. That is also for continuous. But which one was used for categorical data? It was also regression. Which regression? It was named after the function. Go ahead. Now, chi-square is a test or a model? Yes, it is. Yes. Okay. It was logistic regression. Okay. Other name is logic regression. Logistic or logic. Okay. The function is slightly different. Okay. But it's used for the same thing, for categorical value. Okay. So if all of them they apply to same type of or they have some assumptions. Okay. So I was talking about we have some tests and we have some models. In models we have options. For models we have options. Okay. You can go for statistical models or you can go for AI models. Okay. The statistical models have assumptions or not? Statistical models, they have assumptions or not? Yes, they have. AI models, they have assumptions? No. Okay. So the type of data does not usually matter with that. Whether they are following normal distribution, not normal distribution, whatever. Okay. So in terms of models, I can be relaxed. Okay. That I have another whole field where I can do the modeling. Okay. Now those models can indirectly tell you if this variable is affecting or not. If this thing is equal to this or not. Indirectly. Because you have to develop the model and you will use the model to see, okay, this one has more importance, this one has less importance, this one has more effect, this one. Okay? So this is indirect, and even for that, you cannot do it directly. We talked about ANN a lot in my lecture, and we have covered it in that course as well. So ANN does not give you an equation, okay, this one is negative, this one is positive. It does not give you equation like this. You have to do analysis, further analysis to find out these things. Okay. So with AI models, I have an option to do some more analysis and find out about the different effects of variables on the parameters. Okay, the things which are usually very clear with the statistical model because of the equation. Okay, so the same thing can be done. But for tests, there is no alternative. Okay, so we have statistical tests which can apply to normal data or any other type of data. But we don't have AI tests. You're getting my point? We don't have AI tests. That okay, instead of t-test, let me do a ANN test. Or let me do a something test. There is no such thing like this. Getting my point? Okay. So for testing purposes, we always go for statistical tests. Okay, but the statistical tests we have discussed up to now, they have the most important assumption of normal distribution. Okay, so if this assumption is not valid, I need an alternative within the statistical tests. Okay, so we will discuss those tests now. Okay, so those tests which you can use as an alternative to t-test, ANOVA, and whatever test we have discussed earlier, are called non-parametric tests. Okay. So non-parametric tests are those which are, they are also called as distribution-free tests. Okay, distribution-free tests. So because they do not depend upon the central limit theorem. Remember central limit theorem? What was it? In the center and central limit theorem applies to normal distribution. First you find out it's normal. Central limit theorem does not say this is normal. Central limit theorem says if it is normal, then this is true. What is true?
That it has the dimension.
No, that is normal. You were saying something.
Yeah, it's made sure that it's normal, but because of the multiplication, plus or minus the standard.
Yes. Yes. Having normal distribution is a condition for central limit theorem. Central limit theorem does not tell you it's normal. Central limit is applied when it is normal. Are you getting my point?
The 95%.
Yes, 95%, 99.9%. Okay. So central limit theorem will apply if it is normal. Okay. So if the data is not normal, then central limit theorem will not apply. If central limit theorem does not apply, you go for non-parametric tests. Okay. Distribution-free tests. Okay. Now, what are the conditions where you can do, where you can go for, or how do you select where I should go for parametric test or non-parametric test? How do we decide? These are some conditions which help you decide. Some conditions. Okay. You have very small sample size. Okay. The inherent assumption of normal distribution is having enough samples. With few samples, a very obvious thing is I cannot draw the curve of normal distribution. There are 3 points, 5 points. There is no curve. Okay. So with very few, you cannot do it. Okay. If you have rankings, okay, what we are calling it, nominal. If you have nominal variables, 1, 2, 3, 4, 5, then you will not, obviously you will not have normal distribution. It will not make any sense. Okay, either the condition is good or either the condition is bad. It will not be somewhere in the middle. Okay, getting my point? Okay, so I give you a questionnaire to rate different courses from 1 to 5. Okay, 1 is very bad, which you will give to my course, and 5 is very good, which you will give to I don't know. So, but you will be on one side, right? Okay, it will not be in the middle. Getting my point? Okay, so ordinal data, it does not, it will definitely not work. Interval or ratio data, this is where it's tricky, because this is very clear. How many samples you have? Less than 30? I can say. type of variable is different, is ranking or 1 to 3 or any other form of nominal, it makes sense. Okay, it will not be known. But this is where it is tricky, because the variable is a continuous variable. Okay, and you may have enough observations as well. But when you look at the observations, it is very much skewed. I believe this is, yeah. So when you try to plot it, it looks something like this. Okay, so the type of variable is correct, the observations are correct, number is correct, but when you see the distribution, you don't see any normality there. Okay, so in that case, again, you can go for not normal or non-parametric test. Okay, and this is basically interlinked. Okay, so a condition like this will happen when outliers have a lot of effect. So in this case, you can see the lower values have a lot of effect. So the distribution is skewed towards the lower side. Okay, and similarly it can be towards the higher side as well. In some cases, it happens just because of some outliers. Here you can see some values, right? Okay, there are a lot of values on this side, so the whole distribution is skewed. But in some cases, I have very few values, but those few values have a lot of effect. Okay, so and that happens when the difference between the outlier and the other value is like very large. Okay, so you keep on, for example, there is something where you can have a negative answer as well. So that one negative answer will have a lot of effect on all the positive values, because you are subtracting it. You get the point? Okay. So if any of these conditions are seen in the data, then you should go for non-parametric tests. Okay. The interesting thing is, if you go for non-parametric test, there is no argument. There is no argument against it. If you go for t-test, somebody can argue this will apply, this will not apply. If you go for non-parametric test, there is no argument. Nobody can know why you do this. I didn't. Because they are free, so they can go anywhere. Okay, they can apply to a variable which follows normal, and they can apply to one which does not follow. Okay, so whenever you are in doubt, you go for non-parametric. Got it? Okay. So, but the problem is they are said to be having less statistical power than t-test or ANOVA. They are considered less reliable than t-test or ANOVA. Okay, but if you don't have any chance, then obviously this is your choice. Okay, so some practical examples. For example, you have crack per meter data on the pavement. Okay, so this will be highly skewed data. Okay, because number of cracks in 1 meter. Any outlier will have a lot of effect on it. Okay, you're looking for every meter, and you have cracks, so there will be some pavement sections which will be having very high number of cracks, and some may be very smooth. So the data will be skewed. Okay, you are doing subjective ranking for surface roughness. This is done. There's an example later on as well. Okay, so again, this is ranking, rating. So you cannot go for parametric testing. Okay, so how do these non-parametric tests work? They don't work on values, they work on ranks. Okay, so non-parametric tests work on ranking of the values, not the value itself. Okay, so the highest value goes at the top. Okay, and the lowest value goes at the bottom. It doesn't matter what exactly is the value. If the highest value is 2, it will go at the top. The next value, if it is 1.9, it will come at second place. If the next value is 1, again, still it will come at the second place. Okay, so the value does not matter, its rank matters, order matters. Got it? Okay, so when you are working on ranking of the value or the order of the value, okay, not the value itself, then mean will not be used. So we will use median. Okay, so median is the middle value, right? So the ranking will give you the middle value exactly. Okay, we don't have to go after the mean. Okay, as I mentioned, they are more robust to outliers and normality assumption. So you don't have outliers, you have outliers, this should work. If you have normal, you don't have normal, this should work. This is our main advantage why we apply them. The disadvantage is, as I already mentioned, they are considered less accurate, less powerful, and usually they need more data. Okay, because now the data is skewed, so there is no assumption behind it. Okay, so you need or you should have more data. Okay, and they are less informative because median is less informative than mean. Median is less informative than mean. Okay, because if you look at these values, 1, 5, 7, 8, 10. Okay, what is the median? Okay, so until I insert a value maybe 6 here, this median may not change. Okay, but the mean, if I make it 2, will the median change? No. Will the mean change? So mean is more sensitive to the values, which is an advantage as well as disadvantage. Okay, advantage because it is affected by all the values. When you get one value of mean, you know that the entire data is covered. But with median, it's just a value in the middle. Okay, got my point? So this is the problem with these tests. Yes. Larger sample you get more power. You can still use a less sample, no problem. Okay, because there is no assumption behind it, so it will still work. Okay, but larger sample gives you more confidence. Okay, so some how the ranking is done. Okay, some examples for that. So we have crack width data. Okay, so you can see that the data is highly skewed because you are measuring the crack widths. Okay, so most of the times the crack widths are very small. Okay, so the data will be highly skewed on one side because most of the data is very small. Okay, but then we have two values which are very, very big. This is 10 times bigger, right? We have 0.1, 0.2, and suddenly we get 1 and 2. So this is 10 times bigger. So if you plot this, it will create a skewed data set. For example, if I take these values, (0.1, 0.2, again 0.1, 0.3, 0.4, then 0.2, 0.1, 1.5, and 2, and 0.3. Okay, so now you can see the data is very much skewed. It's not the right sort of graph. Sorry? I believe histogram. Yes. Sorry, it's putting there two groups. Anyway, so this is like, again, two groups means it's a good indication of the skewness of the data. If the data is normally distributed, you will see more groups being used. Okay, but here, you see most of our data is in a very small group, and this is basically all the other values, and this is the last two values. Okay, so this is a very skewed data. If the data is not skewed, you will see more even bars. Okay, bars will be very close to each other in terms of height. Okay, every group will have similar number of values. Okay, so most of the values were near zero, but there was some values which are very far from the zero because of the two readings. So in this case, if you apply the mean will be destroyed because of these two values. Okay, if you calculate the means, it will be destroyed because of those two values. So median could be a more robust, more practical approach to calculating this. And then you have the pavement surface rating. Okay, so the rating goes from 1 to 5. Okay, so you are driving the car. It's a test which they do. Okay, it's a real test. Okay, so when you have to measure the surface of the road, okay, in terms of the roughness, they do test. They drive the car on it, test cars, and the people who are in the car, they rate the roughness of the pavement and can go from 1 to 5. So they did it for maybe different segments. Okay, for the same segment multiple times. Okay, maybe. What is it written here? From 1 to our data is ordinary, we can't calculate. Okay, whatever. They did not mention if it is one segment or multiple segments. But anyways, again, if you calculate the mean, you can see the mean is 3.25. Does this value have any practical implication for this data? No. 3.25, either 3 will make more sense to me, or 4 will make more sense to me. 3.25 does not tell me anything, because what can I say? I have 25% more roughness than 3? No. 3 means a condition, right? 3 is one of the conditions. 1 is a condition, 2 is a condition. But 3.25 is nothing. Okay? So that's why here in this case you will also go for non-parametric test. Okay, so this is the first example data, the crack width data. So this is the raw data. Okay, and this is the sorted out data. Okay, so now you can see some of the values are repeated, right? Okay, so any non-parametric test which is working on this data will do the ranking something like this. Okay, so the values are repeated. So how many times it is repeated? 3 times, right? Okay, so rank number 1, 2 and 3 all are same value, right? So all will be given the same rank. Okay, which is, how do I get 1.5? It's the middle. Okay, then you take the middle. Same thing here. So 1, 2 and 3 are gone, so the next is 4 and 5. Okay, so again you take the middle and it's rounded up and so on and so forth. And then you have these and so on. Okay, so the main thing is that the data is ranked, and whenever you have repeated values, okay, they will have the same rank. Yeah, the test will do everything for you. Okay, the test will do everything for you. But I'm just giving you an example of what is happening inside the test. It will sort out the data and assign rank to the data. Okay, and the test will be performed on the rank. Okay, the rank. Okay, one of the very common non-parametric tests is U-test or Mann-Whitney test, also called as Wilcoxon rank sum test. Lot of names for the same test, so you can imagine how popular it is. Okay, Mann-Whitney U-test or Wilcoxon rank sum test. Okay, so this is used as an alternative to t-test. Okay. Now, what was the purpose of t-test? What were we testing with t-test? On which data you will apply t-test? What will you have in your hand? You will say I will do t-test on it. Mean of what? Standard deviation of population. Okay. Anything else?
With the data and comparison.
Compared to what?
The standard deviation.
Of. So I need two data sets, right? For comparison.
Yes.
Okay. So t-test is used for comparing two data sets. Indeed.
Yeah.
Okay. If it is parametric. If it is non-parametric, you will use. Okay. Mann-Whitney test for the same thing. The purpose is same. I have two data sets which are non-parametric. I have to compare. If it was parametric, I will use t-test. If I am comparing two data sets which are non-parametric, I will use Mann-Whitney test. Got it? Clear? Okay. So again, you know the null hypothesis that the groups are same. Okay. In this case, because we are not looking at the values, we are looking at the ranks, right? So the ranking distribution is same. In this case, the null hypothesis is the ranking distribution both data sets is same. So we are not testing if the means are equal, we are testing if the medians are equal. Okay, and this is the code which does the Wilcoxon test for you in R. Okay, so here you will have the variable, and here you will have the categories. Okay, so we have the strength of concrete, and we are trying to test if different mix types have the same median of the strength. Okay, so here the variable you are testing, and here the variable which is the difference between them. Okay, and you will take the data, the concrete data. Okay, so before that you have to read the data. This command will not work. Okay, you have to do the read of the data. Okay, you can try this one. This one will create a skewed data set, and then you can test it as well. So there is no need command here. Okay, it will work as it is. It should. Inshallah. Yes, what happened? Yeah, the data is skewed. Okay, and for side A and side B.
So it's
The alternate hypothesis is
it's true, they are not equal.
they are not equal. Okay, and how do I know that?
Because
If it was not written, then how do I know that?
true location shift is not equal.
No, let's say if this statement was not written, how do I know that null hypothesis is accepted or rejected?
From
Well, what did it run?
Yeah, I'm reading. You just.
The code ran?
Yeah.
Okay. So if the statement is not written, then how do I know that median of side B is significantly greater than side A? From which number?
The p-value.
The p-value. Okay, the p-value. The p-value is how much?
0.05.
0.05 something. Okay, so anything 5% or less means null hypothesis is rejected. Oh, sorry, null hypothesis is rejected.
Or less or more, because this is more than.
Sorry?
It's more than 0%.
It's more than 0.05.
0.05.
Exactly.
So do we.
So 0.05 is basically when you accept the when you reject the null hypothesis. At 0.05 you can reject the null hypothesis. Exactly 0.05 you can reject the null hypothesis. Or lower.
And higher we will accept.
Yes. So you look at the U value. How much is it? What W value?
It's actually
120. So obviously it's a very high value, right? So there is a very high difference between the ranking of the median between the two data sets. Okay. So when you look at the value, it will start making sense. Okay. So if you are ever confused about the p-value, look at the value of the statistic. Okay. In this case, it is W. We have used F statistic, T statistic. Okay. So you look at the value, it will give you a very clear indication. Okay, whether I should accept it or not. So the difference between them, W is like a difference between them. You see the difference between them is 128. Okay, so it's a lot of difference, right? Okay. So in this case, we are basically accepting the alternate hypothesis. We are rejecting the null hypothesis. Okay. So p-value exactly 5% is considered as acceptable for alternate hypothesis. Got it? Okay. And I told you in some cases, even if it was 6%, you can still say, okay, it's true at some level. The alternate hypothesis is accepted at 6% level. You can say that this is also allowed. Okay. As long as you are showing the p-value and you are making a result out of it, and you are showing that I am making this result at this value, this is allowed. Okay? Okay. Even up to 10%, some people do it. Some people do it even if p-value is up to 10%. They say, okay, I am accepting the alternate hypothesis at 10% confidence. So whatever he is saying, he is showing it. Got it?
So
Okay.
if it's less than 10%,
In some cases, they say, okay, we will accept the alternate.
You're saying if it's less. No, if it's more, you accept the null.
If it is more, I accept the null. So if it is less than 10%, see what the usual confidence interval is 5%, right?
Yeah.
So we were saying 5% or less.
For
alternate, for accepting alternate.
But here it's more. We were saying 5 or less for accepting null.
Yeah.
5 or less for accepting null. 5 or more?
Yes.
I mean more than 5.
So it's this is what I'm saying. In some cases, like, it's how much more than 5? 0.24, right? 0.24%. 0.24%, right?
So we can accept the null.
We-
It's not.
Yeah, we are exactly at the borderline. This is what I'm saying. We are exactly at the borderline. Okay? So we can go both ways in this case.
Then when we will reject this is then 0.
If it is less than 0.05% or 0.05 or 0.05 exactly, we will reject null hypothesis. Okay? This is normal. This is the hard rule. Okay? Now you can follow the hard rule exactly, or you can make some margin for you. Okay? So in this case, you are very close to 5%, right?
Yes.
Okay. So should I reject the entire data because of 0.25%? It doesn't make any sense. Okay?
We can accept the null in this case.
We can accept the null.
We can accept
We
the
can
null
accept the
and
null.
reject the null.
We can reject as well.
Or we can say we will stick to the 0.005
Yes.
exactly and reject the null, accept the alternative. Yes, same as the
Yeah. Yeah. go beyond this point. Okay, point. You can go up to 10% as well. In some cases, people go up to 10%. Then they say, okay, I am accepting the alternate hypothesis at 9% confidence. Okay, the point you set, you can set your own limit if it is reasonable. So up to 10% is considered reasonable.
Because you have 90% confidence.
90% is a lot, right? It's a lot, it's still a lot. Okay, so up to 10% is still considered reasonable. The main point is not the limit itself. The main point is how you report it. Okay, so if you only gave me the result, the last line, I will not accept it. Maybe it was only 1%, not even 5 point something percent. Maybe it was 0%. You have, if you have seen previous tests, some of the tests, we got something e to the power minus 17 or something. So p value was exactly 0. Okay, up to 17 decimal places it was 0. Okay, but even in that case, if you give me the answer without the value, I may not accept it. Okay, but even if you violate the 5% limit by 1 or 2%, you can still enforce your answer with better reporting. You're getting my point? Okay, so it's not only about giving the answer, it's about how you report it. Okay, you have to be careful about reporting the answer. You have to be transparent and clear. I'm accepting it at this level. Got it? Okay. Okay, another test we have is called Kruskall Wallis test, which is used as an alternative for one-way ANOVA. We did not discuss two-way ANOVA or something. We did? Two-way ANOVA? Two-way. Okay. So in two-way you can look at two variables at a time. One way only for one. There is no three-way ANOVA. Okay. Anyways, what was the purpose of ANOVA? What is the null hypothesis in ANOVA?
That's all the variance is same as the
How it is written?
mu is equal to
What is mean? Mean. We are
Mean
testing it through variance, but the hypothesis is mean. All means are equal, right? Here, same thing. All medians are equal. Okay, but it's more than two groups now. For two, you will use the U test like we did. Okay, so it's more than two. Now, same thing which we do with ANOVA. If it's more than two, we use ANOVA. This two, we use t-test. Same thing here. Okay. So, and this is so distribution of all groups are equal. And again, we are saying distribution, but we are testing the distribution through rank and median. Okay, like we were doing it for ANOVA using values, right? So here we are using the rank and the median. Okay, so distributions are equal, distributions are not equal. Okay, you can do this. So this is the R code which can do it for you. Okay, so this is the variable you are testing, and this is the factor which is dividing them into different types. The different types of bolts. So that means we have more than two types of bolts. That's why we are doing Kruskall Wallis test. Otherwise, we will do the Mann-Whitney test. Okay. So you have the bolt type data. Okay. You can, but first check. I believe you may have to install this library. FSA. This is an install command, right?
we have to read also
We have to read this, yes. The bolt, and you have to set the directory first. Then you have to do the read command, and then you have to, if you are maintaining a file, maybe you have the read command for the bolt type data. You just copy the entire command and use put it. We have used it earlier. Did you install the library? Okay, so you can see that how it is doing the ranking. Okay, it's taking the differences between them. And first of all, what are the results for Kruskall Wallis test? So it's comparing between the means, right? It's comparing between different group types. No, but it should have done the Kruskall Wallis test first. This one. Okay, now, okay, this one. Okay, so the Kruskall Wallis test gives you if there are any median which is different than the others or not. So we have four types of fold types. Yes. Okay. So we have four. So the first of all, we have fold type A, B, C, and D. So there are more than two groups. We can use Kruskall Wallis test. We did Kruskall Wallis test. It gave us the p-value. How much? How much is the p-value? So you see 10 to the power minus 6. So it's almost 0. Okay. Or it's 0. To the sixth decimal place it is 0. Okay. So now we know that the four bold types have at least one difference between them, right? Okay. And then we do the done test, which will tell us which one of them is different from the other. Okay. So we have the A and B. Again, you can for each comparison, the p-value and the z-value is given. Okay. So you can see which one is different from the other. All of them are different. All of them have a p-value less than 5%. Yeah. 8 to the power. Okay. So all of them are. There is no single pair which is same as the other.
Except this.
Except this one.
A and D.
Well, 6%, right?
Yeah.
6%. What about the other one after that? This one as well, right?
It's point 0.03 to the minus 2. So
0.03 or 7?
0.02. This one, you mean this one?
No, I mean the
Oh,
one
yeah,
above.
7, yeah.
7,
Yeah,
right?
so
6 and 7%.
So B and D and A and D.
So yeah, A and D are similar to each other. B and D are similar to each other. The other pairs are different from each other. Okay.
But shouldn't this mean that A and B also are similar or not? Because they're
If what is similar?
A and B and A and D.
If A is similar to D and B is similar to D,
So A should be similar to B.
yeah,
It's not.
in some cases maybe yes. Okay, well the test shows that it's not like a must.
Yeah.
You can have different, you can have similar. Okay, the adjusted p-value and the p-value, the difference is the adjusted one takes into account how many values you have. The unadjusted one doesn't take into account the number of values. Okay, so that's why we look at the adjusted p-value. Okay, I mentioned this last time when we were discussing the correlation. The correlation coefficient which we use, which we have used earlier, is called Pearson correlation coefficient. Okay, Pearson correlation coefficient, the one which we have used with the regression previously. That is parametric. If you have non-parametric test, okay, and that one measures linear relationship between the two variables. Okay, how much is the linear relationship between the two variables? But if it is not linear, then you will use Spearman rank correlation. So again you can see that it's working on rank, not values. Okay. So it can work on linear and non-linear. It is an alternate to Pearson correlation, and you can use it when you know the relationship may be non-linear or maybe the data is ordinal, okay, or nominal or whatever. So you can use when the data is not continuous. So you can use Spearman. I mentioned at that time we use Spearman for non-continuous data, for categorical data, nominal, ordinal. You can use Spearman. This is how I have used it. Okay, but they are saying if you can use it for non-linear data. So I don't know how it works, but you can. Okay, so this is the syntax, the code which can do the correlation, Spearman correlation for you. Okay, and then you have to specify the method here. I believe the equation which we have used, the code which we have used earlier, it was without this one. So it was taking the default correlation as Pearson correlation. Okay, but again you have to load the command. This one will do the correlation between load data and deflection data. Okay, so beam data is a full data set. In that full data set there is the column of load, and that full data set we have the column of deflection. We are comparing between them using the Spearman correlation. Okay, and if you look at the file, you have already used this file earlier, I believe. You will see that both these are continuous variables. Obviously load and deflection is continuous, right? Okay, but why we are using Spearman here? Because why are we not using Pearson correlation, the one which we already used with regression? Why are we using Spearman here? Why? We already use, or we have already studied this one. No, because we expect that the relation can be non-linear, okay, between load and deflection. And you may have seen the equations between load and deflection in the structures. They are non-linear equations. So this one may give you the wrong impression. It can give you a very low value, not because there is no relation between them. It is because the relationship is non-linear. Getting my point? Okay. So you have to be careful of which one you are using, or you can use both of them, and you can see. Even if one of them is higher, that means there is a relationship, right? Okay. Or like I said earlier, this one works in both cases. If somebody used this one, it will work with linear and non-linear both. Okay. Another example is between river flow and suspended sediment concentration is also non-linear. Okay. People who are in water resources, they would know that, or AI would know that, and somebody can copy it. Okay. So if you have to choose the right test, you can look at this flow diagram, or you can simply go with these rules. If you are comparing two independent groups, you can do t-test or Mann-Whitney test. If it is normal, you go for t-test. Not normal, Mann-Whitney test. If you are comparing more than two groups, you can do ANOVA or Kruskall Wallis test. Again, normal, not normal. If you are comparing relationship between two variables, okay, they are related or not difference. The first two are for difference. The third one is if there is a relationship or not. If you expect linear relationship, you can go for Pearson correlation. If you are expecting non-linear relationship, you can go for Spearman coefficient. Okay. So for example, now you have to choose your test in each scenario. So there are some scenarios given, and you have to pick your test. These are the things which you can look for in the scenario. If normal distribution, if it is skewed or not, if the data is ranked, if the sample size is small or whatever. Okay. So you have to look for these keywords. So we have a civil engineer who is checking the roughness or smoothness of the road surface, and he is doing the IRI meter test. Okay, so it's a test, it's a real test. All these examples are real. Okay, but we have nothing to do with them because we will not be in this. Okay, but anyways, so the I values for method A are highly skewed. Okay, because a few sections had placement issues. So for some of the sections, these values are very high. For other sections, they are not so high. Okay, so the data they did it for 15 sections, and they have 15 values with method A, 15 values with method B. They are using two different methods, okay, of asphalt paving, okay, and they took 15 values with each of them, each of the methods. Then they have to compare between the smoothness of these two methods, okay. So we have two methods first of all, and we are comparing between two. So what are your options? Mann-Whitney or Mann-Whitney or
T-test.
T-test or Mann-Whitney test, right? Because we are comparing between two.
Yeah.
Okay. So which of them tells me I should use Mann-Whitney test or T-test?
It says smoothness is measured, so I think it's ranking.
It's ranking, but they are using a meter. So the one which I was talking about, that is the ranking one. The example that I gave earlier. So people were ranking it. Here they are using a meter. So meter can give you any reading, right? It's like a thermometer.
Yeah, but maybe it's
Not maybe. Maybe. What is this?
So it's maybe
Yes, it's not ranking. From meter, I can say it's not ranking. Meter does not do ranking. Otherwise, what's the point of having a meter?
T-test.
T-test, sure. What else can you look at? Like I said, you have to pick the keywords here. Look at the statement.
It's highly skewed. That's
It's
why.
highly skewed. Okay, so we will go for which one? The other one.
The Mann-Whitney.
Mann-Whitney test? Okay. Don't write in the exam, the other one. Everything will be the other one, huh? Thank God those students are gone. Otherwise they will pick the trick. The other one. Okay. So we will use Mann-Whitney test because the data is skewed, not because it is ranking. Okay. It's not ranking because they are using a meter. Okay. Compressive strength of concrete. So then there is no ranking, right? Compressive strength of concrete. Okay. There are 30 samples for each of the mix. There are 3 mixes. Okay, they are testing the 28-day compressive strength of 3 new concrete mix designs. Each design has 30 samples. The data for all 3 mixes follow the normal distribution. Variances are approximately equal. Okay, you need to check if the design methods are causing some significant change in the compressive strength or not. First of all, tell me your options.
It's 3, so it's.
It's 3. So we can have
ANOVA
or the other one.
Kruskall.
Okay. And which one?
Each with.
Huh? ANOVA.
I think that they are following the normal distribution. But the
Okay,
sample
then-
size is
30.
but it's still big.
30 is like, exactly. Yeah. We have done ANOVA with less than 30 samples as well. Like people don't argue. Maybe because they don't know. But I have seen that. For lab experiments, they do that. Okay. In some cases, with less samples, because it's a lab experiment and the lab experiments are standard tests. So we have a standard like ASTM standard, right? So ASTM has given you a procedure. They tell you, okay, use this machine and the samples size should be this much height, this much diameter, and so on. Okay. So in that case, even if you brought 5 samples of each type, it may still go with ANOVA. Because the procedure which you are using is already standard procedure. So getting my point? Okay. If you you did something on your own. I made one questionnaire myself, and I collected the data from people, different people. Okay, now I have less samples. I'm trying to do on the wire. Then there's a problem. Because you develop your own method. With the standard methods, the parametric tests are allowed because with low samples as well. Because the method is already tested. People know when we follow this method, we have normal distribution and the variance is so on. Got my point? Okay. So in this case, ANOVA. Okay, what about this one? Safety performance. The inspector, safety officer is going from one site to another site. At each site, he is giving them a number from 1 to 10. Based on composite score of health and safety records, near misses of the accidents and the audits which are done on the site. So he takes all the record into consideration and he gives a number himself. Okay. So ordinal ranking from goes from it's an ordinal ranking data from 1 to 10. Okay. So the ranking he is giving is 1 to 10. He is doing it on 10 sites, but each site has a number between 1 to 10 in terms of safety. What we want to check if the safety ranking is related to the company size. So some of the sites are managed by small size companies. Some of them are medium. Some of them are large size companies. Okay. So we want to check if the data is related to company size. This ranking, which he is doing from 1 to 10, is it related to company size? First of all, what are we checking here?
Check the output is categorical.
Huh?
Output is categorical.
Output is? Output is categorical.
We are having ranking, so it's non-linear.
Non-linear. Non-linear?
No, ranking, so it's non-parametric. Yes.
Non-parametric. Okay, but what are we testing here? Like, what test will I apply? Tell me. What test or what? Which one? What are the options?
Either Kruskall or Wallis.
Okay. Because there are three types of companies. That's why
They are not comparing, but it's
they're not comparing.
maybe it's the one which is child. I don't know what is the name.
Chi-square test? Chi-square test? How?
Because the output is categorical.
Huh?
Output is categorical.
Output is categorical. Yes. That's very good. So you were saying what? Kruskall Wallis test. You were saying what? Kruskall Wallis test. And you are saying you can do chi-square as well. Okay. And what else? Anything from today's lecture? Huh? ANOVA?
No, the last one. Spearman.
The Spearman ranking. Okay. How will I apply Spearman ranking here? Tell me.
Because it's not linear.
No, how will I apply it?
Oh.
See, correlation, how do we apply correlation? We have one variable, another variable. What is the correlation between them, right? What are the variables here? Tell me. Correlation between what?
Safety.
Safety ranking
Yeah.
and
And then the company size.
company size.
Yes.
Safety ranking is ordinal, right?
Yeah.
And company size is
Also,
ordinal. So you are comparing between two ordinal variables. Okay, so we can do Spearman, no problem. Okay, we can do Kruskall-Wallis test. We can do as an alternative to ANOVA because we have three groups. So you will take the company, the ranking according to each company. So you will have three groups of values, and you can compare between them using Kruskall-Wallis test. Okay, and we can do chi-square test as well. Now, how will I apply chi-square? How will I apply chi-square? You are the one who mentioned. You have to answer this. How will I apply chi-square test here? Chi-square test checks what?
to check that if the safety is related
How?
It's,
What is
it's
the,
independent or not?
sorry,
Independent from the safety or not?
how will I check it? What is the null hypothesis? Give me a sentence. What is the null hypothesis?
That they are independent. They are, I mean, they are dependent.
Right.
Following the size, community size.
Huh?
That there is a relationship between them. This is the
That is the correlation coefficient, right?
yeah.
But how the chi-square works here? Chi-square can work, first of all. Chi-square can work, yes. But how will it work? What am I checking?
The distribution.
The distribution, right? If chi-square test works, then distribution should be
Similar.
similar, right? So the distribution of sites having a particular ranking for a small, medium and large size company will be similar to each other if they are independent of each other. Okay, if the company size does not have any effect on the safety ranking, then the chi-square test will show that these three have similar ranking. Okay, but the problem with chi-square is you have to do pair by pair.
Same as.
So you have to do multiple times. Okay, you have to do multiple times. So you are compare between small and medium. Chi-square can compare two at a time, two distributions at a time. You compare small with medium, you compare medium with large, then large with small and so on. Got my point? Okay, so it's like a longer route. Okay? Okay, water infiltration rate example. A geotechnical engineer measures the water infiltration rate, which is in centimeter per hour, in a field treated with 3 different soil amendments. So they did some changes in the soil to decrease the water infiltration rate, and then they took the readings with each method. So there are 3 methods, remember. The data appears normal, but the sample size is very small, only 5 measurements for each method. Okay, infiltration rate for 5 samples from amendment A, B and C. This is my data. So total 15 samples, one with A and B and C. Okay, we have to compare the effect of 3 amendments on the infiltration rate. Okay, we have to compare the effect of amendment on the infiltration rate. I have 3 of them, 3 amendments. What are my options? It will not be lower. You can use the other one. Not the other one. Kruskall Wallis test. Okay. Yes. Because they are saying the measurements are very few. Okay. And if it was a concrete lab test using EST methods, I could have applied ANOVA as well. This is what I explained earlier. Yeah, if it is, no. With 5 samples, using standard testing methods, ANOVA can still be allowed. This is what I said. In this case, basically we will go for Kruskall Wallis.
Because
Okay.
what you mean with the standard, it will be normal.
Yeah, we can make an assumption that even with few samples, it is.
It's normal.
It's an assumption. Okay, so we can make an assumption if the testing procedure is as per standard and people already used it and people already found it is normal. Got my point? Okay, now we have pre and post retrofit deflections. You know the meaning of retrofitting, right? Dr. Ajmal's favorite term. Retro means going back. And fit means fit. So now we will do like this. So why don't you start with R means what and E means? It's not like dimension code. Retrofit means what? What is retrofitting means? You are repairing. Okay. So there's a beam. Okay, you see a crack. Okay, now it's a building. So what do? You cannot just replace the beam. You will do retrofitting. Okay, you will repair it. You will do something on it to repair it. Okay, so retrofitting is you do something on the top to repair it. Because it's a beam, you cannot like go inside it or something. Okay, so you do something on the top to make sure the crack or whatever the deflection or whatever is under control and does not go worse. Okay, that is called as retrofitting. Okay, as Dr. Ajmal's favorite topic. Okay, like he likes to break things and then same as his sons. You have seen that? No? Okay. So they did retrofitting on a bridge. They found some cracks or something, some damage. They repaired it, and they took the deflection readings before and after. Okay, for 10 bridges at the middle span. Okay, before and after and they want to see. So they have paired measurements before and after paired measurements. Okay, for 10 bridges. Determine if the retrofit significantly reduced deflection or not. Okay, now this one I believe we did not discuss in the class the answer to this one, so I'll explain myself. Okay, but before we do that, let me give you the concept why we are going for the new test here. It's not a new test, it's a variation of the old test. So for example, I have deflection from bridge 1. Okay, so I have 10 measurements before, 10 measurements after. Okay, each one is for a different bridge. Okay, it may happen that bridge 1 had initial deflection of 0.1 inch. Okay, and after the retrofitting, it may have gone to 0.08, from 0.1 to 0.0. Okay, bridge 2, it may have an initial deflection of 0.05. After the retrofitting, it goes to 0.04. Okay, so if I combine all the bridges together, and I come before and combine all of them after, and if I compare between them, okay, so maybe the one which was having 0.1 will affect this entire data set. It will affect this entire. I'm taking combined mean here. So when I take the combined mean, that one bridge can affect the mean for all the bridges, right? And that includes the bridge which has an initial value of only 0.05. Getting my point? Okay? And the same thing will happen in the after as well. If I look at the bridge which has 0.05 initial and 0.05, 0.04 final. Okay? And I combine it with the bridge which had 0.1 initial and 0.08 after. Okay? So if I combine between them, I'm combining two very different things, right? Okay? So in this case, I cannot combine all the readings and calculate one mean, because each reading belongs to a different case. A different bridge, right? A different bridge which has its own initial and which has its own final. Okay? Got my point? So I cannot reject a retrofit because of, I may say, okay, the mean before is 0.08 and the mean after is also 0.08. Okay? So, okay, the retrofit did not have any effect. It might have had an effect if you were taking it from bridge to bridge. Each bridge may have its own effect. On each bridge, it may have its own effect. Okay? But when I combine all of them, the mean could come out to be same. What do I mean? Okay? So in this case, I have to combine between each pair of them. I will compare the before of the bridge with the after of the same bridge. Okay? So this is called as the paired test. Okay? Measurements are paired. So I can only combine or I can only compare between the measurements which are of the same unit. Got it?
So we'll have 10 pairs.
We have 10 paired measurements. Okay? Before and after. Okay? We cannot combine these 10.
This test, it will show
Now we have to apply a test which can take these measurements separately, each wrist separately, okay, as a pair of measurements. So that test is called as paired t-test. Paired t-test, but it's not the same t-test. It's paired t-test. It also works on ranking and difference. So it's also non-parametric. Paired t-test is non-parametric. Okay, got my point? That's why we are discussing it here. It was not part of the slides. But here, only that one will work. Normal t-test will not work, and the Mann-Whitney test will also not work. Okay, because of the problem that you cannot combine different units together. There is a pair of measurements which belong to the same unit, and you have to consider it as a pair. One pair cannot be mixed together. Got my point? Okay, so the method which we apply is called paired t-test. It's also, no, Mann-Whitney does not do the pairing. If you are going to take one data set complete, other data set complete. As a group. Okay. So only paired t-test can do that, and paired t-test is non-parametric because it also works on ranking and differences. Same as Mann-Whitney. Same as that. Okay, clear? Okay, this is the thing. So if you want to test for something, if it follows normal distribution or not, this is a test for checking the normality of the data. If the data follows normal distribution or not, you can have a look at it in R. Okay, how the test is applied and so on and so forth. And if it, then you can select which test you want to apply. If it follows normal distribution, you can apply t-test. Does not follow normal distribution, you can apply the Mann-Whitney test and so on and so forth. Okay. Try to write it as a paragraph. Okay. The correct, like we discussed in the previous lectures. I give the format, right? And that format will not change. The name of the test will change. That we are testing this with this test. But it does not mean that you will change the reporting style. The reporting style will still be complete, the p-value and so on and so forth. And the good thing is with every test you can see there is a p-value, there is a statistic, there is a null hypothesis, there is an alternate hypothesis. So the statement can remain the same. You just plug in the values and the name of the test and so on. Okay, so let us take a break for the prayers, and after that